In this last section of Chapter 2, we're going to take all these ideas and processes for taking derivatives and apply them to velocity and acceleration problems. This final section will feel a little bit like a physics class. So, how do we find instantaneous velocity, which is a rate of change? Well, if you think back to the beginning of this chapter, we found that the derivative answers the question of finding instantaneous rate at a given point. But before we get into those details, let's talk about velocity a little bit. Velocity, like you might have seen in other classes prior to calculus, is a rate of change, and it's the change of position with respect to time. So in those previous classes, you would have been finding something called average velocity. And your equations probably looked a little bit different than what I'm about to show you. But what it is it's a change of position with respect to time. I'm going to put a change of x in the numerator because usually in calculus we have things moving along the x-axis. So of course the position would just be an x position. So it's the change of position with respect to time. If you want to take that a little bit further for a more complete formula, what we're saying is we're taking an x value at some time 2 minus another x value at some time 1, and then dividing that by the difference in those times. The next thing we need to talk about is acceleration. Well, velocity is the rate of change of position with respect to time. So acceleration is the rate of change of velocity with respect to time. Velocity is the thing that's changing when we're talking about acceleration. And again, before this class you would have seen average acceleration. It's the change of velocity with respect to time. So it's the change of velocity over the change in time. And again, if you want a more complete looking formula for that, we'd have the velocity at some time 2 minus the velocity at some other time 1 divided by the difference in those times. But in this class, we're not really so concerned with average velocity or average acceleration. We want to find instantaneous velocity, which again we know deals with a derivative. So first things first, usually in calculus our position functions are shown as x of t. Most problems in calculus we have some sort of particle or object moving along the x-axis, so of course its function would be x. It's somewhere on the x-axis. It's depending on where the particle is, that depends on time, so it's going to be the position function x of t. So using that, how would we find our velocity function? Well, we know that velocity, or we know that finding instantaneous velocity is done by applying the derivative. So to find our velocity function, we need to take the derivative of position. The derivative of position is velocity. So how can we extend that idea one step further? Well, to find acceleration, what we would do is take the derivative of velocity, or the second derivative of position. So acceleration is a interesting idea. Velocity is easy to see. When something moves, it has velocity. So cars driving down the street, you're walking, what have you. Acceleration is a little bit different. It's something that you can really feel, I suppose, in a manner of speaking. Acceleration is a little bit harder to see visually unless it's kind of the extreme case. Using the car analogy, if a race car accelerates very fast from a dead stop, you can definitely see that acceleration. Or conversely, if there is a crash and there's a sudden stop in a car moving, you can definitely see that deceleration. So pretend that you were jamming the brakes of your car. You are definitely going to feel a change in velocity, which we call acceleration, as seen by this silly little animation here. Okay, so that kind of covers the basics of what we need to know, or some of the concepts of what we need to know. Our position function we're going to call x. To find our velocity function, we're going to take the derivative of position. And to find our acceleration function, we'll take the derivative of velocity. Here's a little extra piece of information. Please note that this little purple box here is just some extra information, just to be a little complete here, but you'll never see this in AP Calculus. Are there more things after acceleration? Well, the answer is yes. If you take the derivative of acceleration, you'll get something that is called jerk or jolt. After that, there's actually another thing after jerk. If you take the fourth derivative of position, or take the derivative of jerk, you'll get something called jounce or snap. And the list kind of goes on and on, but these two in purple are just to kind of give you a complete view of what's going on, but we'll never really use those in this class. Okay, so let's keep our discussion going with this idea of moving in one dimension. Again, we're going to be moving on straight lines, and that's usually along the x-axis. So how do we define velocity being positive? Well, if you ever see velocity being positive, you're going to know that your object, your particle, whatever the problem's talking about, is moving to the right. If we're talking about a vertical motion, we know it's going to be moving up. Opposite to that, if velocity is negative, if our particle is moving horizontally, like on the x-axis, it'll be moving to the left. If our particle is moving vertically, like along the y-axis, it'll be moving down. If velocity is 0, of course, the particle's motion, the object's motion, is stopped. Nothing's happening. Speed. Speed is a little bit different than velocity. Velocity indicates direction, but speed does not. So if you ever need to find speed, as sometimes on the AP test, what you need to do is take the absolute value of velocity so you can get rid of any possible negative signs. So speed does not indicate direction, so that's why we take the absolute value of velocity so we ensure that it's not negative. The last thing we need to realize, and I think it's kind of one of the easier concepts to not understand fully, is what if acceleration is 0? All that means is that velocity is not changing. It does not mean the object has stopped. If velocity is 0, we know the object has stopped. But if acceleration is 0, all that means is that we're moving at a constant velocity. Okay, so we have a big problem here. We're going to attempt to fill in this table. What we're given here is that we have a particle moving along a horizontal line, and it has a position function, x of t equals t squared minus 4t plus 2. So you can see that our position function is called x because it's moving on a horizontal line, which is of course the x-axis. So what we want to do is complete the chart for the first 5 seconds of this particle and show where the object is on the number line below. So you'll notice in the table we need to find velocity and acceleration, so we're given our position function. So to find velocity, we need to take the derivative of position. But you'll notice I didn't write it as x prime. I just know that velocity is x prime. It's much more convenient to write it as v instead. So to get velocity, we take the derivative of position, and in this case that's 2t minus 4. To get acceleration, we take the derivative of velocity. The derivative of velocity in this case is 2. So now let's start to fill in the table. So how do we determine what the position of the particle is at time 0? Well, we're going to take that time 0 and plug it into position. If you plug in 0 into the position function, we'll get 2. So we know the particle is at the point 2 on the horizontal line x. So I'm going to put a green dot down there just to keep track of the beginning point for this particle. Velocity. To find velocity, we'll plug in 0 to our velocity function and we'll get negative 4, which is telling us we're moving to the left. If I want to find speed, I take the absolute value of that velocity, which is of course 4. The acceleration is a interesting answer, I suppose. We didn't end up with a function that has a t in it. So basically what this is telling us is that acceleration is always 2. We can't plug in any times, so acceleration must be always 2. Doesn't matter what time we're looking at, it's always 2. So how can we describe the particle's motion? Well, we see from before that our velocity is negative, so we know it's moving to the left. So I'm going to put a little arrow to the left down at the bottom. Okay, I'm going to move a little bit faster in filling in this chart. Just kind of keep in mind the way we get these numbers is we take these times that we're looking at and we plug them into our equations over here that we found. Okay, so let's kind of go through this chart a little quicker now. At time 1, our position is -1, which is great because we knew we were moving to the left. So I'm going to put another dot down here at -1. Our velocity is -2, which is indicating we're still moving to the left. Our speed is 2, the absolute value of that. So how can we describe this motion? Well, we're still moving to the left because our velocity is negative, but just a little bit slower. We went from 4 to 2, so we're still moving left, but it's a little bit slower. Okay, put an arrow going to the left at the bottom. At time 2, our position is -2, which makes sense. We were moving to the left, so our next point should be to the left. Our velocity in this case is 0 now, which means our speed is 0. So how can we describe the particle's motion here? Well, if velocity is 0, the particle has stopped. Okay, what about time 3? Well, it says we have a position of -1. So I'm going to go ahead and put a dot up at -1. Our velocity is now +2, which means our speed is +2. So you'll notice something very important has happened. We're now moving to the right. Our particle has changed direction. We were moving to the left, but now after we stopped, now the particle is moving to the right. So I'm going to kind of keep on going on this particle's journey here and showing those arrows. What about at time 4? Well, position is 2, which makes sense because we're moving to the right. So I'm going to put a dot at 2. Our velocity is +4, and our speed is +4. So how can I describe the motion here? Well, since velocity is positive again, we know we're still moving to the right, but faster now. We went from 2 at time 3 to 4 at time 4. So we know we're still moving to the right, but a little bit faster. And now to finish this, at time 5 we have a position of 7, so that means we're still moving to the right, which means our velocity is positive, in this case 6. Our speed is 6. So how can we round out this story of the particle? Well, we know we're moving to the right still, but since we went from 4 to 6, we're going even faster now. So we went from 2 to 4 to 6. So in this last description, we're still moving right, but a little bit faster. Okay, continuing on this straight line, one-dimensional motion, we are generally interested in when an object is stopped or when it has no acceleration. In general, not all the time, but in general. But we're also interested in when objects are speeding up and slowing down. A lot of the times this will be asked of you on the AP test. So we need to realize some things. An object's velocity is either positive, moving right, negative, moving left, or 0 if it's stopped. If an object's acceleration is positive, that means there's a pull to the right. If the object's acceleration is negative, there's a pull to the left. And if it's 0, we just have constant velocity. So we're going to fill in this table that will list all the possibilities of an object's motion. In this first box, what happens when velocity is positive, which means we're moving to the right, and acceleration is positive, which means there's a pull to the right? Well, in that case, concerning speed, the speed would be increasing. If we're moving to the right and we get shoved more in the direction of going right, we're going to increase our speed. Conversely, if we're moving to the right and our acceleration is negative, we get pulled in the opposite direction, we're going to slow down. Our speed will slow down. To fill in this last box in the row, if velocity is positive but acceleration is 0, all we know is we have constant velocity in the right direction. Okay, now what about velocity being negative? Well, if velocity is negative, we're moving to the left. But if acceleration is positive, that's a pull to the right, which is in the opposite direction, which means our particle is slowing down. What if velocity is negative, which means we're moving to the left, and acceleration is also negative, which means we're being pulled more to the left? Well, that would tell us that our speed would be increasing in that case. In the last case, if velocity is negative and we're moving to the left and acceleration is 0, all we know again is we have constant velocity, but we're moving to the left because velocity is negative. In this last row, velocity is going to be 0. What does it mean for velocity to be 0 for acceleration? Well, it means nothing, really. If velocity is 0, it doesn't matter if acceleration is positive because the particle is stopped. If velocity is 0, it doesn't matter that acceleration is negative because the particle has stopped. And of course, the same can be said if acceleration is 0 when velocity is 0. Okay, so let's take a look at some one-dimensional straight line motion. We have a red sports car traveling, and its position is P, and it's measured in miles, and T is measured in hours. And we have the position function for this sports car, t squared minus 7t. The first question is this: when, which is a time, when is the car 30 miles from where it started? Well, we have a position function, and we know the position of this car, and we want to find when, which is a time. So we know the position P is 30, and we're trying to find the time when that is 30. So we have a quadratic equation, and just as a reminder, when we have these quadratic equations, we have to set them equal to 0. Move everything to one side and set that equal to 0. We need a factor after that and set both of our factors equal to 0. You'll notice we get 2 times. T is equal to -3 and T is equal to 10. One of those answers is an extraneous nonsense kind of answer. We know time cannot be negative. So how long does it take the car to get 30 miles from where it started? Well, it takes 10 hours. Second question: what is the velocity at the very moment the car is 30 miles away? Well, we know that it takes 10 hours to get 30 miles away. So we want to find the velocity right at that point. Since we have our position function, we know from that first slide that the derivative of position is velocity. So P prime is equal to our velocity function. And I'm putting P prime here, but I would prefer that you really don't write P prime. We know that velocity is the derivative of P, so it's better just to write V, but it's okay to write P prime. Our velocity function is 2t minus 7 when you take the derivative. We want to find the velocity when the car is 30 miles away, which happens at t equals 10 hours. When you plug in 10, you'll find that that answer is 13, and the units would be miles per hour for velocity. The last question is, when does the car stop? Well, just like you've seen in some of the previous slides that we've been talking about, is when velocity is 0. When velocity is 0, we know our particle, or in this case, the car has stopped. So since we know our velocity function is 2t minus 7, we need to set that equal to 0 so we can figure out when velocity is 0. Of course, that's an easy little equation to solve. We see that the time when velocity is 0, or when the car stops, is at 3.5 hours into this trip. Okay, next example, a little bit tougher. We don't have a sports car here, but we have a particle traveling on a horizontal line. Of course, t is greater than 0. It's kind of just some extra information there, but of course time is greater than 0, and its velocity function is given below here. And we're measuring this in meters per second. We want to find any time that the particle changes direction. So a couple slides ago, we kind of tracked this particle in a table to see what was happening, and we noticed something. A change in direction occurs only when velocity changes from a negative to a positive. In other words, it stops. It has to stop to change from a negative to a positive, or vice versa, if velocity changes from positive to 0 to a negative. So that's a very important idea. If we want to find when a change of direction occurs, velocity is going to have to change from a negative to a positive, but in between it's got to stop. If velocity changes from positive to negative, and in between it stops or is 0, we know there was a change in direction. So how are we going to determine where this particle changes direction? Well, the very first thing we have to find is when it stops. When does the velocity equal 0? If it ever equals 0, then maybe it does change direction. So let's see, what times do we have for when the velocity is equal to 0? Well, when we set our factors equal to 0, we'll get 2 times. T is equal to 2 and t is equal to 5. So we know this particle stops at 2 and at 5. So how are we going to determine if this particle indeed changed directions at either 2 or at 5? Well, I'm going to set up a little table here. We know that time is starting at 0, of course. It can't be negative, so since time starts at 0, we have some regions of movement. We know from 0 to 2 seconds, it's moving. And then at 2, it stopped. We know again it started moving at 2, but at 5, it stopped again, because velocity was equal to 0. And then after 5, it just keeps on moving. So, does velocity change from negative to positive, or positive to negative? Well, let's see. I'm going to take some time in between 0 and 2 and plug that into our velocity function. V of 1 means I'm taking 1 and plugging it in to, again, this velocity equation up here. So, what do we get when we plug in 1 into our velocity equation? Well, we're going to get negative 12. So what does that mean in terms of movement? Well, since velocity is negative, we're moving to the left. But that's not enough to determine if there was a change in direction. So let's do the same thing for 2 to 5. I'm going to pick a time between 2 to 5 to see what the velocity is. And of course, a good choice would be 3. I'm going to take 3 and plug it again into this velocity equation. If you plug 3 into the velocity equation, you'll get negative 6. So our velocity is negative. So did a change in direction occur? Well, no. We went from a negative velocity, stopped, and still kept going negative after that. So there was no change in direction. Okay, now let's try a time after 5. Of course, you're free to pick any time after 5, but keep it simple, and we're going to choose 6. I'm going to take 6, plug it again into my velocity function, and I'm going to see that I get 48. I don't really care that 48 is what I got. I care more that that is a positive velocity. So did a change in direction occur at t equals 5? Well, yes. We went from negative velocity before, right here. We stopped. And then after the stop, we went to a positive velocity, which means there was a change of direction. The particle changed direction at t equals 5 because velocity changed signs. Okay, next example hopefully does not apply to you. The title is The Disgruntled Calculus Student, so hopefully this class isn't making you like this student in this example. So suppose a disgruntled student is tired of AP Calculus and goes outside to throw their calculus book as hard as they can into the air. So we're going to be given some information about this book in the air. The position of the calculus book is going to be P, and that's going to be equal to negative 16t squared plus 96t. T is seconds, P is in feet. So I'm going to give it a little graph here just to get a visual, and you can see that this book goes in the air and of course it's going to come back down based on this position function. So the first question is this: what is the maximum height attained by the book? Well, first things first, you can label this graph in your notes. There is an upward velocity and a downward velocity, of course. The book is thrown straight up into the air, and then it comes straight back down. But we know something. We know at the very top of this traveling motion, at the maximum height, the velocity has to be 0. Why is the velocity 0 at that maximum height? Well, there's a change in direction. When the book is thrown up into the air, it has to stop just for a split second before it comes back down. So we know the maximum height happens when velocity is equal to 0. So we don't have a velocity function, but we know the derivative of position is velocity. So again, I'm going to put p prime of t, but I think it's actually better just to put v. But I just want to remind you, v of course is obtained by taking the derivative of position, which in this case is negative 32t plus 96. So we want to find when is velocity 0, so we can find our maximum height. So we can solve this equation quite easily, and we'll end up with the answer of 3 seconds. But it didn't ask when. The question asks what is the maximum height? What is the height that the book gets to? Well, we know the time when the book gets to its maximum height, so how do we find the position at that time? Well, we're going to take our position function and evaluate it at that time. If we plug 3 into our position function and evaluate that, we'll find that the position of the book at time 3, or the maximum height, is 144 feet. Question 2. At what time does the book hit the ground? So, do we need velocity in this problem? Well, not so much. We know, as you can see in the animation here, that when the book hits the ground, what is its position? Well, when the book hits the ground, it has a position of 0. It starts at 0, the disgruntled calculus student throws it up, and then it comes back to where it started, which would be a position of 0. So this actually really isn't a calculus problem. We don't need to do any calculus to answer this question. We want to find when is p of t equal to 0. So we can take our position function, set it equal to 0, and factor the position function, and set both of the factors equal to 0. We'll get t equals 0, and when you solve negative 16t plus 96 equals 0, we'll get 6 seconds. So that makes sense. At t equals 0 is when it started at position 0. After 6 seconds, it's back to position 0. It hit the ground. So that's our answer. At what time does the book hit the ground? Well, it takes 6 seconds to come back to the ground. Question 3. How fast is the book moving when it hits the ground? In other words, what's the velocity of the book when it hits the ground? I would say that there's a very common mistake that many students can make here, and that would be to guess or assume that the velocity of something when it hits the ground is 0. So to kind of clarify, we're really talking more about the instant before it hits the ground. What is the speed of the book? Well, we know that it takes the book 6 seconds to come back down to the ground, so we're really asking to find the velocity at 6 seconds, because that's when the book hits the ground. So we're going to take our velocity of 6 and plug it into, our time of 6, and plug it into our velocity function, which will give us negative 96. The units are going to be feet per second. Why negative? Well, it's because the book is coming back down, which is a negative direction. So it's a downward direction, which makes our answer negative, and that kind of verifies that. One last little follow-up question. We want to find the acceleration of the book. Keep in mind, to find acceleration, we need to take the derivative of velocity. And to take the derivative of velocity in this case, it's nice and quick. The derivative of velocity is negative 32. But note the units. The units on acceleration are feet per second squared. Velocity has just feet per second. Acceleration has feet per second squared. So if you weren't aware of that, please make note of that unit on acceleration. In these last 3 slides, we're going to attempt to tackle a complete AP test free response question, which is calculator allowed. And it's a very short question in a sense. We have the time period from 0 to 5, and we're given the velocity of a particle moving on a straight line as v of t and equals that equation right there. So we have the velocity equation. So part A, we want to find all the values of t from 2 to 4 for which the speed of the particle is 2. So even though the complete story, so to speak, of this particle is from 0 to 5, we just want to find the times from 2 to 4 for which speed of the particle is 2. So as a reminder, speed is the absolute value of velocity. So we want to find when does the absolute value of our velocity function, which is that long function right here, is equal to 2. So if you've been practicing using your TI-89, you might be very tempted to do something here. You might be tempted to type this equation into your calculator and use the solve command. Well, you could try that, and I've done that on this problem, and it takes the calculator quite a while to compute this answer. That's not necessarily the most elegant and effective way to solve this problem. So as you can see in this note here, many, not all, calculator allowed questions can be solved graphically instead. So when you end up with these kind of crazy looking equations, you can try using the solve command, but it might freeze up the calculator, and of course on a time test you'll be losing precious moments while that calculator is trying to solve a long, difficult problem. So we're going to attempt to do the graph instead. And throughout all these steps you're going to see in these next 3 slides, I should point out, please pause the video and attempt to do these along with me on your calculator if I'm moving too fast for you. So let's go ahead and graph this function. And you'll notice in my graph here, I've only graphed the piece of our function from 0 to 5. There's no point in graphing all the extra stuff. Let's just focus on 0 to 5. So it's not labeled, of course, on the calculator, but my window, I adjust it to be 0 to 5. So that's 1, 2, 3, 4, 5. Okay, so how are we going to do this problem? Well, we need to find when this graph, which is our absolute value graph, is equal to 2, which means I need to find when the line 2 crosses with my absolute value graph. So that extra line I drew in right here is the line y equals 2. Okay, so if that's the line y equals 2, from 2 to 4, how many times does our 2 graphs cross? Well, they cross twice. Once over here and once over here. The one time it crosses over here doesn't count. It's not in the window. It's not in the interval that we're looking at. Okay, so if you're good with using your calculator, you should already know how to find where those 2 points are. If you haven't been practicing using your calculator, again, take a moment to kind of follow along here. So how do we find intersections graphically? Well, first, we're going to go to F5, and you'll notice that choice number 5 says intersection. The first thing that you're going to be asked to find is the first curve, and it usually will choose it for you. Just verify that it's choosing one of the curves for you. So select either graph as the first curve, and then it's going to ask you for the second curve, and then of course choose the other graph as the second curve. Okay, so now we got to choose which intersection point we're looking at. I'm going to try to find this intersection point first, this one right here. Don't worry about the other one. You'll just have to repeat these steps to find the other one. So I'm going to try to find that intersection first. So it's going to say select a location for the lower bound, which means put the little blinking dot just to the left of that intersection point and press enter. Then it's going to ask you to find the upper bound, which just means put your little cursor just to the right of that intersection point. If everything goes good and all works out after you press enter, you'll get your intersection point. In the case of this first intersection, we get 3.12763, but we're just going to keep 3 decimal places, so 3.128. If you repeat the steps to find the intersection point over here, you'll find that that's 3.473. Okay, part B of this question says, find all the times t from 0 to 5 at which the particle changes direction. Then we need to justify our answer. So how are we going to do this problem? Well, for a particle to change direction, we need to see the velocity change from negative to positive and in between pass through 0, or see the velocity change from positive to negative, but in between stop or become 0. So what would be the best way to approach this problem? Well, again, we can kind of take care of a piece of this problem from the get-go. Since we're being asked to justify our answer, we can kind of get that out of the way right away. When the particle changes direction, the particle changes direction when the sign of velocity changes. So we've kind of already answered one piece of this problem. Even if we didn't know how to actually find those times, as long as you just know that fact, you can at least answer a part of this and get some points. So we know a particle changes direction when the sign of velocity changes. So let's actually find the time or times that happens at. So the way we're going to approach this is graphically. We need to visually see when does velocity actually change signs. So when does velocity change signs? Well, again, I've only graphed our velocity function from 0 to 5. We don't really care much about what's happening outside of that range or that window or interval. Okay, so we can see that the velocity changes signs in 2 spots. The velocity changes from negative to positive right here, which means there is a change of direction, and velocity changes signs right here from positive to negative. So again, we know there was a change in direction. So how do we find those 2 points? Well, now this is just, again, up to you in terms of if you've been practicing using the TI-89. So how do we find those x-intercepts? How do we find those zeros graphically? Well, if you go to the math option F5, you'll notice that choice 2 is to find a 0. So how do we find a 0? Well, what it's going to ask you to do is to pick a lower bound. So what I'm going to do is try to find this 0 first. We can't find both at the same time. So I'm going to just try to find this one first. So it's going to ask us to choose a lower bound. So we need to put our little cursor just to the left of our x-intercept, or 0, and press enter. Then it's going to ask us for an upper bound. We need to take our cursor, put it to the right of our x-intercept, or 0, and press enter. What we're doing is we're giving the calculator a little window to search for the 0 in. After you press enter, it's going to tell you where that x-intercept, or where that 0 is. And in this case, of this point, it's 0.536. Again, remember we have to round to 3 decimal places. To do the second 0, all you need to do is repeat that process that we just went through, and you'll find that the 2 times when the position of the particle, or the particle changes direction, is 0.536 and 3.318. Okay, last part of this free response question is part C. Is the speed of the particle increasing or decreasing at time equals 4? And we need to give a reason for our answer. So to determine if speed is increasing or decreasing, we need 2 crucial pieces of information. We need the velocity and we need the acceleration at that time. So let's get the part out of the way that we can get done pretty quick. We know our velocity equation is given above, so if you use your calculator and use the little bar or evaluate button to do this, the calculator will plug in 4 for you. So if you've been practicing using this stuff, it should be nice and simple. So when we plug 4 into our velocity equation, we'll get negative 11.476, which just means the particle is moving to the left. But to determine if it's increasing or decreasing in terms of speed, we also need to find acceleration, which means we need to take a derivative of velocity. And unless you want to do this derivative by hand, I would not suggest doing that. This is a calculator allowed problem, so now I'm going to give you guys the ability to take derivatives on your TI-89. So it's a really easy process. All you're going to do is, instead of going to F2 like you've been doing hopefully and practicing some of this stuff under the algebra tab, now we're going to go to F3, and the very first option is to take a derivative, differentiate. So there's a format that you have to type this in, and it's a very simple format. After you choose number 1, which is to take a derivative, all you're going to do is put your function in the parentheses with a comma x and close those parentheses, which is just telling the calculator to take the derivative of whatever function you want with respect to x. So just as an example, if you want to try this out and pause the video at any time, I want to take the derivative of the function that you see here. So you'll notice I did something. I didn't actually type the function into this line right here. Again, if you've been practicing using the calculator like I like to use the calculator, I'll first type in the function all on its own just to make sure I didn't make any mistakes. Usually mistakes start to happen when you try to type everything on one single line. So what I'm going to do is first type in the equation, make sure it looks like the equation I should be taking the derivative of, and it does. And then I'm going to just take advantage of using that answer key, the second answer key. And you can see this is the d from our notation that we need to use. This is our function, which is used in place of this little answer here, and then comma x. If you press enter, it'll give you the derivative of the function that you typed in. One big note to make: now that you're able to take derivatives in your TI-89, you've got to be careful. In some cases, the answer that the 89 gives you might not look like the answer you'd get by hand. So use some caution when you're trying to check your answers using the TI-89. Even though you might think you have the right answer, you might, but it might not match the TI-89, even though both are the right answer. So be very careful of that. Okay, so if you're okay with this process of typing in to the calculator to find a derivative, now we can do that to the problem at hand. We know our velocity function, and if you type that in and take the derivative, like you can see I did right here, this part down here is our derivative. And you'll notice there's a little arrow here, which means there's still some more stuff hidden to the right, but we don't really care about what's over there. All we want to do is we want to take that answer and evaluate it at 4. So if you type all that in and everything works out, you'll find that your acceleration at time equals 4 is negative 22.296. And with that, we can finally answer this question: is the speed of the particle increasing or decreasing at time equals 4? Well, we know that the speed is increasing at time equals 4 because velocity and acceleration have the same sign.